Welcome to the second session on functional realization using gates. In the last presentation, we had seen how a sum of products function can be realized using the basic gates. We also had a quick look onto the product of sums implementation. In this session, we'll see some more examples on product of sums realization, and we'll also see how either of these functions can be implemented using the universal gates. The second example is the implementation of f is equal to a plus b plus c into a bar plus b bar plus c into a plus b bar plus c. The first term is a plus b plus c and is implemented using the first OR gate. The second term is a bar plus b bar plus c, which is implemented by using the second. Third term is a plus b bar plus c, which is again implemented by the third OR gate. So, the third type of problem is implementation using a specific gates. Normally, implementation using an universal gates is desired. So, we'll see how any expression can be implemented by using a NAND gate. The example which has been taken is f of a comma b comma c comma d comma e. Look, it is a 5-variable function is equal to a plus b bar plus c into d bar plus b e bar using only NaN. So the step 1 is implement it using any gate as we had done in the previous examples. A quick recap again on how an OR and an AND can be constructed by using only NaN. Look at the first expression, an OR. A plus B is the output of this OR. Consider the De Morgan's theorem. A plus B is equal to A bar into B bar, the whole bar. So take a NaN. Inputs to the NaN should be A bar, B bar. So both the terms or both the figures are the same. An OR can be constructed as a NaN gate with a bubble at the output and two bubbles at the input. Similarly, an AND can be constructed as an OR with two bubbles at the input and a bubble at the output. So the step 2 in the implementation using only AND gates. Step 2, convert AND gate into NAND gate. But how? A bubble is deliberately introduced at the output of the AND gate. And the step 2 in step 2 again, to compensate for the bubble, the input of the next gate is also introduced with a bubble. Step 3, look for the gates. If a gate has one input with a bubble, the other input is also introduced with a bubble, right? In order to compensate for the bubble, the output of the preceding gate is introduced with a bubble or complement the literal. Now look at this figure. The two bubbles which have been marked do not have a preceding gate. Step 4. If an OR gate does not have a bubble at either of the inputs, bubbles are introduced and are appropriately compensated. Step 4. If an OR gate does not have bubbles at either of the inputs, bubbles are introduced and are appropriately compensated. So consider this OR gate. In the previous slide, there were no bubbles at the input. So bubbles are deliberately introduced. What do you mean by appropriately compensating? When you look at the previous slide, you can see that the inputs to this OR gate are B bar and C. Since bubbles are deliberately introduced, we invert the two literals and they now become B and C bar. Step 5, utilization of De Morgan's law. A bar plus B bar is equal to AB the whole bar. So if an OR gate is there with two of its inputs inverted, that can be conveniently replaced with an NAND gate. So in this figure, three OR gates are replaced with NAND gates. The final circuit thus has only NAND gates. Implementation of any circuit can thus be done using only NOR gates. Use the De Morgan's law, make the simplification, and the circuit will consist of only NOR gates. We come to the end of this session. Hope you would have enjoyed it. Thank you.